Time out. No.
See? No one's ready.
I'm ready. All right, I'm ready.
Okay, I'm ready.
Okay. So, concavity. Basically, concavity is another way to help you sketch graphs. So it's another tool. Okay, so we just talked about increasing and decreasing intervals. So we can find out a lot about a function through increasing and decreasing slopes, like the general shape. So concavity kind of helps us go a little bit further with that. Has anybody heard of concavity before?
One time.
Where have you heard it? I see a few people.
Like concave?
Okay, if you haven't heard of it, shh. I heard people who have actually seen it. Alana, you said you have seen it.
But I don't know where.
Where you heard it? Okay, what about you, Anthony?
Pretty sure I watched a video about it on Concavity.
You don't know where you've heard it? Has anybody heard of it in like science class, like the curvature of light? Yeah.
I just said
convex.
concave.
Well, you're just talking a lot, so sometimes I just tune you out.
I said it 3 times.
Okay, good job. All right, so there's 2 ways for concavity in math to exist. So you're going to have concave up. Okay, so this is what I would write down if I was you. Okay, so concave up, okay, is basically if your second derivative is positive. Okay, so greater than 0. Okay, and concave up is a graph that kind of looks like a smiley face.
That's nice.
Okay, so for example, a parabola, just a regular x squared function, would be a concave up graph. Okay, so we're talking about the curvature of the function. Concave down is if your second derivative is less than 0. Okay, and that would look like a sad face.
All right.
Okay, so concavity is referencing happy faces and sad faces.
Well, that's lovely.
Sound good?
No, I'm not ready.
Okay, so the second derivative test, that's just basically what I just wrote up there. So
What is the I of the big I?
I is representing your open interval, which means your function is just between like it can't be a defined interval, like it exists between 2 and 5. It has to be like from negative infinity to positive infinity, so it's open. Okay, so you ready for an example? How do we find concavity? Okay, so the first part of this is going to simply be asking you to figure out where the function is concave up and concave down. Okay, so how do I find concavity? What do I do?
You take the derivative.
Okay, so we derive it one time, which, by the way, the first derivative tells us about what?
The velocity.
Okay, if you're talking about movement, but if you're just talking about the graph of the function,
I don't know how to do velocity.
it's talking about slope. Okay, so we can use the first derivative to talk about the slope of the function, which is helpful if we are graphing. Derivative of my function is what, by the way? 3x squared. Okay, and my second derivative is going to tell us about the curvature, the concavity of it. So what is the second derivative? 6x. So all I'm going to do to find my critical values for concavity, or again, set it equal to 0, just like I did for increasing and decreasing intervals, and that will help me find my critical values. So would you agree that my critical number would be 0? Okay, and again, I'm going to use a number line test, just like when I was finding increasing and decreasing intervals, and do the same exact thing. So if I choose a value that is less than 0, such as
-0.1.
okay, or just -1 might be a little easier for the brain. Remember that I'm going into my second derivative function. Okay, so if I plug in -1, would I get a positive or a negative number? A negative. Okay, and if I plug in a positive number such as 1, I would get a positive. Okay, so I would have a sad face, and then I would have a happy face. Okay, so to identify my intervals, I could say this is concave up between which intervals? From 0, whoops, that's not a 0. Second what?
So your first derivative is for the slope.
Correct.
Your second derivative is your concavity.
Concavity, right.
And then you find your critical numbers and you plug those numbers in like smaller that you're going to into the concavity.
Right. So whatever thing I'm analyzing is the derivative that I'm using. So I'm using my second derivative to analyze concavity.
That shows a hard one.
Okay. Now I just want to show you what this looks like, just so you understand what the concavity is looking like. Okay. So if I draw this, we know that an x cubed function looks like what? The John Travolta. Okay. So it looks like this. So remember how I said concave up is a happy face?
Yeah.
Okay, well if you put your hands like this and create a happy face, there's actually two sides of a happy face. There's one side that has a positive slope and one side that has a negative slope. Okay, so this particular John Travolta only has the increasing happy face. Okay, whereas the other side is the increasing sad face. Okay, so there's two sides to the happy face and the sad face.
That's that equation or two equations.
That's the x cubed function.
3x cubed, the first.
It's the original function. We're just using all this information to draw the original
So do you have to
function.
write about the graph? Do you have to say anything like
Yeah, we're eventually going to start graphing them. The whole point of this is to graph functions theoretically without a calculator. That's the hope. So at some point I'm going to take your calculator away and ask you to draw functions. Okay, so on this graph there was a really important point, which I didn't talk about. So now we're going to talk about that very important point. So the very important point is called the point of inflection. Okay, and what I would write down for the definition of the point of inflection is when the function changes from concave up to concave down, or vice versa. Okay, so if you want to just say concavity changes, and as long as you understand what that means, it's got to go from a positive to a negative concavity or vice versa.
the concavity changes from a negative?
From positive to negative or negative to positive. Yep. Okay, so if I go back to my function, I'll let you write that down.
Wait, I'm confused. I'm a little confused.
I'll explain it.
So can you say that again?
Point of inflection is when...
Wait, I gotta finish this dumb one and then I'll...
Yes.
So what does tangent have?
Oh, so the tangent line is talking about the slope. Okay, so we also know that those critical values will also happen at a slope of 0. So when we were finding maxes and mins, basically a max and min is only going to happen when the slope changes from increasing to decreasing or vice versa, right? Well, sometimes, I don't know if you ever noticed it, but sometimes there was the scenario where you went from an increasing to an increasing. Okay, and that's where a point of inflection happens. Okay, so this John Travolta is the perfect example of that scenario. Whoa. My slope still increases, although if I took that first derivative and I set it equal to 0, right here, I would have a slope of 0. So if I zoomed in really close to right here, it would level out and have a slope of 0, but it's not a max point, it's a point of inflection. Okay? So, because this function changes from concave down to concave up, we have a point of inflection right there at the point of 0.
Can you say what you were saying again then?
Oh, what's he
A point of inflection occurs when concavity changes from positive to negative. Or negative to positive. Nope, not today.
Okay.
Huh?
From positive to negative
Or negative, that's it. Okay, so we know the x value. How do I find the corresponding y value of this?
You have to plug it into your original.
Back into the original. Okay, so if I plug it back into the original, would you agree that I get 0?
I guess.
Okay. Okay, so those are the 3 pieces that you're basically doing today. Okay, so we're finding intervals of concavity and points of inflection. The first 0 or the second 0? God, good? God. Okay, so let's try another one.
Wait. Can you explain just one more time how you just found
The 0, 0?
Yeah.
See on my number line?
Yeah.
Okay, so since it went from negative to positive, I have a point of inflection at the x value of 0.
And that's your x.
That's my x. To find the corresponding y, I have to plug it back into the original. Okay, we'll do another one here. Okay, so same idea. All we're going to do is figure out where this function has positive concavity, negative concavity, and then potential points of inflections. Okay, so where do I start in doing that? Okay, so we take the first derivative, which would be 3x squared minus 6x. Okay, then to talk about concavity, I need the second derivative, so I will derive again. So what would be my second derivative? 6x minus 6. So now what do I do to find my critical numbers? Set it equal to 0.
No, the first. Not the first. Not the derivative.
Are you talking about the point?
In the original.
Into the original. Yeah. So would you agree that I have a critical number at 1 here? Is everybody okay with that? So now I'm going to do my number line test. Okay, remember that I'm using my second derivative for this number line test. Okay, so a value less than 1 would be 0. So if I plug 0 in, would I get a positive or a negative number? Negative. And if I plug in a number bigger than 1, like 2, would I get a positive or a negative? Positive. Okay, so we have a sad face and then a happy face. So tell me about the concavity of this particular function. So we have a concave, sort of, yeah, down. My pen is not working right.
Why are you plugging it into the second derivative?
Because I'm using the second derivative to find concavity. If I'm talking about concavity, I need to use the second derivative. So from negative infinity to 1, and then concave up from 1 to infinity. Sorry, my pen is being sloppy. So do I have a point of inflection? Where is my point of inflection? 1. Okay, so I need to find its corresponding y value. How do I find the corresponding y value? Plug it into the original. Good. So if I plug that into the original equation, let's see, that would be 1 minus 3 is negative 2, and negative 2 plus 2 makes 0. How are we doing so far? Doing good? No, to find this y value, I have to plug it back into the original. Always plug it back into the original to find corresponding y values. Okay, so we're good with finding concavity and points of inflection. Good there? Okay, so the second half of this is using this information to graph. Okay, so I'm actually going to steal a problem off of the homework here. Actually, I'm going to have you guys write this down first before I do that. Okay, so write this down. This is basically your steps for graphing functions. Okay, so these are the steps that we are going to take in order to graph our function. So when I take your calculator away, you have some sequential steps to follow.
That's one.
So as we go through and do this, we're going to start by using our algebra skills to find information that we can find. And we're going to keep it nice and simple. We're only going to do easy stuff. Okay, and then after that, we'll use calculus to find the next stuff. So we'll use first derivatives to find maxes and mins, and then we'll use second derivatives to find concavity. Right, so critical numbers are where you would have potential maxes or mins, or points of inflection, or potential vertical acid growth. Yep, critical numbers, critical points, yeah. Yep. Point of inflection.
Figured that out right.
As it came out of your mouth.
Yeah.
We're going to graph this, okay? So we're going to find all of those critical values. We're going to find all of our algebraic things that we can find easily and plot them and then draw this function. So first thing I want to do is we want to talk about the domain, okay? So a blanket statement over the domain. When do we have domain restrictions? What are things in math you cannot do? Okay, when you have a square root, because we can't take a square root of a negative, so do we have that scenario? No, we're good there. What else? In the bottom, okay? So anytime you have an x in the bottom, do we have an x in the bottom here? No. So do we have a domain restriction? No. Okay, so we can list our domain as all real numbers. Okay, we don't have any restrictions. Okay, the next thing that is easy to find is x and y intercepts. Okay, now if the x-intercept is easy to find, then we're going to find it. But if it's like super complicated and we get nasty numbers, then we're not going to go there. Okay, would it be easy for us to find the x-intercept? By the way, how do you find an x-intercept? Set it equal to 0 and we would try factoring it. So would this be easy to factor?
No.
No, it's not easy. So we're going to skip the x-intercept part for now. Would it be easy to find our y-intercept? How do you find a y-intercept? When the x's are 0. So if I plug 0 into the x's, is it easy to find? That's pretty easy, right? So we have a y-intercept of 4. Okay, so right now I have a little bit of information. Okay, my algebra doesn't help me a lot. I do know the general shape of this, right? If it's an x to the 4th, what does this look like? A parabola, or potentially like a W. probably a W. Okay, so the next thing I'm going to do is I'm going to start with my first derivative. What does my first derivative tell me about? Tells me about the slope. So I'm going to start by analyzing the slope of this. Where is this function increasing? Where is it decreasing? Do I have maxes and mins? Okay, so remember this very first term, by the way, is the same as 1/4 x to the 4, so don't let that throw you off. Okay, so what is my first derivative? What's that? Good, x to the third minus 4x. Okay, so now to find critical numbers for my slope, what would I do now? Set it equal to 0. I'm going to use that for concavity. We'll do that too. Okay, and then can we go ahead and pull out a greatest common factor here? X. What's left over? Minus 4. And if I set each of those equal to 0, can you jump on that? We have 3 critical values.
Plus or minus 0.
Good. 0 and plus or minus 2. Nice. Okay. So I'm going to use my number line to decide if these are maxes or mins, or maybe they're points of inflections. I don't know. Okay. So remember, I'm using my first derivative, so I'm going to use the factored version. I'm going to use this one to help me with my positive and negativity. So if I plug a value less than -2, such as -3 in, let's see, I would get a negative times a positive, which makes a negative. Okay, then we have, let's try -1. If I plug -1 in, I'd get a negative times a negative, which makes a positive. If I plug +1 in, I get a positive times a negative, which is a negative. And if we plug 3 in, that would be a positive times a positive. Everybody okay with that number line? Okay, so since this is analyzing my slope, I always like to draw this in. This is, in my opinion, like the most informative piece, because that tells me roughly what my graph is. It doesn't show the curvature, okay, but I know that this kind of looks like a W. Okay, I have some maxes and I have a min there. Tell me about where my min is. Or my min, let's go backwards. Where are my mins? Okay, so I have mins at -2 and +2. How do I find their corresponding y values? Good, so if I plug those into the original, let's see, if I plug in -2, -2 to the 4th power is 16. 16 divided by 4 is 4. And then 4 minus 8, right? 4 minus 8 is -4, and -4 plus 4. Anybody else get 0? And you'd get the same thing if you plug in +2, because both those were squared. Everybody okay there? Okay, and I do have a max, a local max. Okay, where's my max at? 0. 0, 4, which is my y-intercept. Interesting. Okay, so once I have my slope figured out, what's the next thing I want to analyze? My concavity. So now I'm going to take my second derivative and analyze the concavity. So what's the second derivative? 3x squared minus 4. What am I going to do with that? Set it equal to 0. And if I set that equal to 0, let's see, you add 4 and divide by 3. And square root u. So we're going to get, let's see, we get 2 over the square root of 3, which we can't leave. Square 3 over 3. 2 square root of 3 over 3. Positive and a negative version. So those are not pleasant, but they're not too bad. Okay, so does anybody happen to know about what the value of 2 square roots of 3 over 3 is? I'll use my calculator to find out. If I can get it to work correctly. There we go. So negative 2 square roots of 3. Nope, that's not a square root. So about negative 1 and a little more. So that helps me with my intervals. So a value that's less than that would be like negative 2. So remember, I'm using my second derivative. I'm going to go to right there to test my positivity or negativity. So if I plug in negative 2, would that be positive or negative? 12 minus 4. Positive. And then the middle of those two would be like 0. So would that be positive or negative? Negative. And then if I plugged in positive 2, that would be just like plugging in negative 2. So this has happy face, sad face, happy face. Do I have any points of inflection? No. Okay, where are my points of inflection? Oops. Negative 2 square roots of 3 over 3, and positive 2 square roots of 3 over 3. So how do I find the corresponding y values? Plug it in. All right, I'll plug this in for us. The good news is they're going to be the same y value. I'm going to type this in like a fraction. So we have negative 2 square roots of 3 over 3, right? Times a fourth. I don't know. I guess I could just do, let's put a 4 down there.
Is that a 3 inside the square root?
Delete. What?
Is that a 3 inside the square root?
Yeah.
How?
Isn't that what we have? Yeah.
I just don't know.
How? Oh, because we had 2 divided by the square root of 3, right? When we solve that equation.
It was 4.
4 was the square root of 4 over 3.
Yeah.
So you got to square root the top. So square root of 4 is 2. Square root of 3 is the square root of 3. But you can't leave a square root of 3 in the bottom, so you got to multiply by the square root of 3 over the square root of 3.
Oh. That's all.
Yeah, exactly. Okay, so then minus 2, and I'm going to use my fraction button again, make sure I type this in right. If I can hit it. Oh my gosh. This would be a lot faster on a regular calculator. Unless somebody else has already got it. Anybody else faster than me? Oh my good lord, come on. I'm going to stick it out. 2 square roots of 3. Oh wait, I need another 2, don't I? No, that's right. No, it's not. Oh my gosh. Hold on, heck with that calculator. And I forgot my exponent, so that's perfect. I'll just do it here. So 2 square roots of 3 over, let's call it 12. To the 4th power minus 2. All right, did anybody else get an answer? I got 1.34. Y'all just gonna trust me? Excellent. Yeah, they're not nice, are they?
I get them and go, no problem. I'm gonna put it in their phone.
That's why I use a calculator. All right, so we got all of our information here. Now we're going to take it and we're going to plot it. Okay, so everything we've kind of mapped out, we're going to plot. Okay, so we have a y-intercept at 4. We have a minimum at -2, 0, and 2, 0. A max, what? Yeah, because they're both going to be squared, so you'll get the same y value. And then your points of inflection are like right there.
This is a big old problem. I like it.
Okay, so at this point, I basically just have to use my knowledge of what this looks like. Since it's an x to the 4th, I know that it's a w. So I'm just going to draw w with those 2 minimum points, a max there. It's going to cross through all those pieces that I found. Like so.
Did you ever finish that basketball movie?
I don't know. Can't remember.
Didn't they lose to Kansas or something? I don't know.
No, they won.
They beat Kansas?
Yeah, they won.
Oh, the dude stepped on the line.
Yeah, that's right. You're right. At the very, very end, it's like, and because he shoots the 3, makes it, thinks he wins, but his heel was out of it.
I hated that movie.
That's not right.
All right. Do you guys want me to do another example of this? Okay. So your homework. Okay, I put this in. So this is what I want you guys to do. I have 2 through 22 evens, but what I want you to do is I want 2 through 22 to be your homework, and then if you want to do 3 through 40, I would give you extra credit for those 5 problems. Okay? So